Okay, good morning everybody. Hopefully I'm on my way home from the airport. Today is 11/1. I'm recording this on Thursday, October 28th, but that's okay, right? We'll just pretend that I'm here with you at this moment, okay? So today, what's our objective? What we want to talk about is rational functions, okay? Rational functions, which are basically looking at graphs and their equations, graphs and their equations of rational expressions. Hopefully you guys remember that if it's a rational function, that means the x variable is in the exponent. So take a look at this. The unknown, which is x, is in the exponent. Now, rational expressions or rational graphs are like, we talked about this also. Either it's going to be exponential that way, exponential growth, or it's possible it could look like this, exponential decay, right? We've seen that before, so let's talk a little bit more about that, okay? So, starting off with these two equations, right? And it depends on which one we want to use. It depends, okay? So we've got fx equals a b to the x, or if x is equal to a times 1 plus r to the x. Now they're basically the same equation, except b as a base looks like kind of the stuff we've been doing, right? That's your base, whatever the base may be, to the exponent, okay? This one is used mostly in terms of percentages, right? So if you're growing at a certain percentage, growing at 12%, or maybe decaying at like maybe half, you'd want to use this one. So let's take a look at example 1. Example 1 says if f of x is an exponential function. Okay, we know that. And f of 0 is 3 and f of 2 is 12. Find f of x. Now it doesn't say anything about percentages. Nothing. This is the percentage one. In fact, let's rewrite that down. Okay, this one is if we have a percent. But this one's if we have a base. So they're different. They're the same exponential, but they're written in different ways. So let's use this one, okay? Because I don't know anything about a percentage. So I'm going to use this one. So I'm just going to write it down. I go f of x equals a b to the x. Okay, so let's see what's going on. Let's just get a visual. 10, 20, 1, 2, 3. F of 0 is 3 is about here. F of 2 is 12 is about here. We know it's exponential, so it probably looks something like that. Ugh, lousy picture. Lousy picture. It doesn't curve very well. So it looks like this. So what is it? What is the exponential function? So if I take a look, I need to know the value of a, which is probably 3, right? And I need to know the value of b. How much is it going up by? So if I use my function, I plug in 0, I get 3. So I'm going to use this first. I'm going to plug in 0 for x and set it equal to 3 because f of 0 is 3. So I'm going to go, okay, let's use this one first. I'm going to go, this is 3, goes for f of x. And I'm plugging 0 for x, okay? So f of 0 means plug a 0 in for x, and it equals 3 because that's f of 0 is equal to 3. And I'm just going to solve for a. Well, I already know it's 3, but let me show you anyway. So 3 is equal to a, and anything to the 0 power is the number 1. Therefore, we know that the value of a is 3, right? Not only that, we can see it anyway from our graph. So let's rewrite our equation, okay? I know this much. I know the value of a. So let's rewrite f of x is equal to, not a, but 3 now. I know the value of a in this example, b to the x. So I don't know the base, but I have more information. I'm given a second piece of information right here. I've got f of 2 equals 12. So if I plug in 2, I'll get a value of 12. So let's put 2 in for x and 12 for f of x. And let's rewrite this second equation as 12, because that's f of x, equals 3 times the base, which we don't know, to the 2 power. So I plug 2 in for x, f of 2, and I set it equal to 12. Okay, now let's just solve, okay? That's easy. Divide by 3, divide by 3. I've got 4 equals b squared, right? Square root, square root. Normally we'd take 2 answers, but in this case we only want the positive. We do not want a negative base, so b is equal to 2. All right, now we have an equation. So it says find f of x. I can write f of x. Find f of x. It's going to be f of x equals a. I know the value of a is 3 times b, which is 2 to the x power, okay? Do not make that 6. That is not 6 to the power of x. That is 3 times 2 to the power of x. Do not multiply those. That's it. Don't make that a 6. That's 2 to the x, not 6 to the x, okay? Anyway, as long as you know that. Now, let's take a look. There's a second piece of this. The second piece is we want to also find f of negative 2. Well, now we can do it. To find f of negative 2, let's just plug negative 2 in for x. So let's say, okay, I want f of negative 2. F of negative 2 is equal to 3 times 2 to the negative 2. So I plugged negative 2 in for x, f of negative 2. And so I'm just going to use, well, I could use a calculator. Sure, it's 3 times 1/4, which is 3/4, or, because that's a 1/4, or just use your calculator. I mean, you can, I suppose. I mean, you know, or you could use your brain. I like using my brain. To the negative 2 power, 0.75, or 3/4. I already knew that. You knew that. Hopefully you knew that. Okay, so that's an exponential function. We got it. Now, let's take a look at example 2. A bank advertised that it can double your money in 12 years. Okay. Find f of x expresses the function of annual growth. What is the annual interest rate? Okay. Now, an interest rate is like a percentage, right? So I'm going to use the other equation. I'm going to go, okay, I'm going to go f of x equals a times 1 plus r to the x power. Okay, now I'm going to change this formula slightly because we're talking about time and amount. So I'm going to rewrite it more as a banking from a of t, amount over time, equals, I'm going to change this to p times 1 plus r to the t. I'm just changing the variables so it makes sense for banking. P is principal. It's still your beginning amount, time, and your rate, okay? So let's see what's going to happen. I know 12 years, that's easy. I can put t for 12, okay? So t is going to equal 12. So I'll put 12 there. So I want to double your money. So if I start with $1, I'd end up with $2. $100, 200, 1,000, 2,000. So it doesn't really matter what you put because you just want to double your money. So I think the easiest is to start with $1 and see when it becomes $2. Or 1 million and make it 2 million. It does not matter. And I'm going to go 1 plus r to the 12th power. Okay, now I just need to solve, right? Okay, to solve then, divide by 1, that seems silly, doesn't it? So I really have 2 equals, that's why I use these numbers, made it easy, okay? 1 plus r to the 12th. I need to solve for r, so I'm going to take the 12th root. The 12th root. Okay, the 12th root will cancel the 12. I'm going to need my calculator. I have my fancy calculator. I'm going to go 12, hit my math button. So I'm doing the 12th root of 2, and I can answer about 1.059. So I get about 1.059 is equal to 1 plus r. Okay, now it's getting easy. Minus 1, minus 1. I've got a 0.059 equals r. Or as a percentage, it's about 5.9% is our interest rate. That's not bad for these days. It's actually pretty good if you find a rate that high. Okay, now, what is the rule of 72? Well, it's a banking rule, and it's a shortcut. This is just a shortcut. If you want to double, it only works for doubling. So we can do this problem faster with a banking rule. So the banking rule is a shortcut. The banking rule says you take your amount of time, which is 12 years, and you divide it by your interest rate, okay? So you want to find out how long to double, okay? So then if I take my amount of time, which is 12, and you divide it by your interest rate, which is our 5.9, okay? Go 12 divided by my 5.9 to get an answer of about, sure enough, it will double, won't it? So it'll take 12 years for it to double, okay? So that's my banking shortcut. All right, now let's go ahead and turn the page and example 3. All right, the half-life, that's a rate. Half-life, that's a base of 1/2. The half-life of a radioactive element is 6 days. In the lab, there's a sample of 100. Okay, write a sample to model this. Now we're going to change our formula slightly. Change our formula slightly because now we have a cycle of time. So if it's every 6 days, that's a cycle of time. So I'm going to change this formula here slightly. Okay, and I'll show you what I'm going to do. So I'm going to say my new formula is going to be my y equals a times my b to the, and I'm going to go t over c, where c is my cycle of time. Okay, so every 6 days. All right, so I put my formula here for an exponential function. A is the beginning amount. Again, I'm going to start with 100 grams. My rate is 1/2 because I'm going to take half of it and half of it. That's my rate, or my b, which is my base. That makes sense, right? I'm going half of it, half of it, half of it, half of it. That's my, it's not growth, but my decay is by 1/2. And then I'm going to go t over 6 because that's my cycle of time. Okay, it's a nice handy formula. Okay, so when you plug in your 20, you don't have to think, okay, how many days, how many cycles. I can just plug 20 in, and it'll tell you how many cycles of 6 this is. So I'm going to plug in 20 into my formula. Okay, so here's my exponential function, and I'm going to use my exponential function. So I'm going to go y equals my 100 1/2 times 20. That's t, time. T is going to be 20, right? 20 days. So I'll plug that in for t, 20 over 6, and I'm just going to use my calculator, right? Okay, I like my fancy calculators. I really do. I know that they're expensive and nobody likes these things, but I do. I like them. So 0.5 to the power of 20 divided by 6. Okay, so this is going to be a cycle of time. How many cycles is 6 or 20? That's basically what I was doing. And about 9.9. 9.92. What is that? Okay, 9.92 is my amount, right? So I went from 100 grams to 9.92 grams of whatever this stuff is. But it can't be good if it has a half-life of 6 days. It's got to be pretty darn radioactive, and that's why we're going to be in a lab. It's got to be nasty stuff. Stuff you wouldn't want to touch or play around with, huh? Unless you want to glow in the dark. I don't know what it is. Okay, example 4. Let's go on to example 4. So here's a chart, and if I look at it, I'm looking for some pattern, and I see right up here, and they tell me that it's got to be exponential because it's a population. So what I see is this. I looked at all my numbers, and what I see is from here to here, I took half of it. Okay? So it took 6 days for us to go from 128 to 64. So that's my cycle of time in this chart. It's not always 6 days, just a coincidence. So my cycle of time, again, is 6, but in terms of days. So it's 6. No, I'm sorry, it's hours. Oh, 6 hours. So let's use the same formulas we did up above, except for it's from a chart. So I start off with y equals some a, b, to the T over C, because I've got a cycle of time, so I want T over C. And let's use this equation. So the half-life is 6 days. We know that 6 days is my half-life. Every 6 days we take half. Oh, look, there it is again, half, right? Every 6 days we take half. So that's my half-life, 6 days. From here to here is half 6 days. From here to here is half 6 days. Okay. Now write a function. Well, that's easy. Y equals the beginning amount. The beginning amount has to be 128. Times, what's my rate? I'm going half for a cycle of time, T over 6 for 6. Oh, I keep saying days when it's hours, isn't it? You guys are probably yelling at me, Mr. Davies, come on, it's hours, not days. Now, I've got my function, and so what I can do then is how many bacteria will remain after on day, but it should be 1 day. I need to retype that. One day, which is 24 hours. So I'll just put the 24, right? 1 day is 24 hours. I'll take the 24 and plug it in there. So I'll rewrite this as y equals 128, 1/2. 24 is my time, divided by 6, which is really 4 cycles. I guess you could do it. You could do it another way, but I prefer to just use my calculator. 128 times my 0.5 to the power of 24 divided by 6, which I know is 4. 24 divided by 6, and I get an answer of about 8. That made sense. So I've got 8, and this term is bacteria. Probably thousands of bacteria, and that's just an abbreviation. Okay, so here's your homework, and please work on this. I'll be back tomorrow, and get this done. Work quietly, and I'll see you tomorrow, okay? All right, adios.